Welcome to part 3 of this video playlist about the best strategies for converting carboxylic acids into acyl chlorides. This presentation is about the use of phosphorus chlorides as deoxychlorinating reagents. These are more reactive than the reagents discussed in part 1 and 2, but are also less selective. Moreover, these generate phosphorus waste, which may be difficult and expensive to dispose of. Nevertheless, there are instances where phosphorus chlorides may offer some advantages. The most common phosphorus-based deoxychlorinating reagents are prepared as shown here. Elemental phosphorus is obtained by reducing calcium phosphate, and its treatment with chlorine yields first liquid phosphorus trichloride and then solid phosphorus pentachloride. Some industrial processes yield phosphine, which can also be converted into phosphorus trichloride with chlorine. Oxidation of phosphorus trichloride yields phosphorus oxychloride. Deoxychlorinations with phosphorus pentachloride give phosphorus oxychloride as byproduct, which can be conveniently removed from high-boiling acyl chlorides by distillation. Thus, one common strategy is to perform the reaction with a solution of phosphorus pentachloride in an excess of phosphorus oxychloride and to isolate the product by concentration of the reaction mixture. To better understand the mechanism of deoxychlorinations with phosphorus chlorides, let's first have a look at the basic reactivity of tri- and tetravalent phosphorus derivatives. Phosphoric and phosphorous acid are not very strong acids, and trimethyl phosphite and phosphate are therefore weak methylating reagents only. Sulfuric acid is 4 to 5 orders of magnitude more acidic, and dimethyl sulfate therefore a strong electrophilic methylating reagent. But methyl phosphate or phosphite are much less reactive and are almost never used for methylations. When trimethyl phosphite is heated to reflux, it undergoes Arbusov reaction only slowly. Cationic tetravalent phosphonium salts with at least one alkoxy group, however, are powerful electrophiles. Thus, if trimethyl phosphite is alkylated, the resulting phosphonium salt is immediately demethylated by the leaving group, even if this leaving group is a poor nucleophile, for instance chloride. This is the so-called Arbusov reaction. Similarly, during the Mitsunobu reaction, a triphenyl alkoxyphosphonium salt is formed, which will immediately alkylate any negatively charged nucleophile nearby, even at low temperature. Interestingly, alkoxyphosphonium salts only alkylate negatively charged nucleophiles, but never neutral ones such as amines or pyridine. This suggests that these alkylations are actually intramolecular processes that proceed by initial formation of a bond between phosphorus and the nucleophile to yield a pentavalent intermediate, as sketched here. Chloride is a weak nucleophile, and acyl chlorides will only be formed from acylium cations or from acyl groups with excellent leaving groups. As shown on the previous slide, dealkylations of tetravalent cationic alkoxyphosphonium salts proceed under mild conditions and even by weak nucleophiles, probably through intermediate formation of a pentavalent phosphorus derivative. Therefore, it is likely that the formation of acyl chlorides from acids and phosphorus pentachloride also proceeds by way of a pentavalent intermediate, as shown here. In the case of phosphorus trichloride, phosphorus would have to be protonated by the acid to yield the required intermediate. This suggests that bases could in fact prevent or slow down deoxychlorinations by phosphorus trichloride. Phosphorus oxychloride is a much weaker electrophile than phosphorus pentachloride or protonated phosphorus trichloride. The ionization potential of phosphorus trichloride is also lower than that of phosphorus oxychloride, what suggests that phosphorus trichloride should be much more basic than phosphorus oxychloride. I could not find any detailed kinetic measurements, but I would expect the addition of carboxylates to phosphorus oxychloride to be slower than the addition to phosphorus penta or trichloride. Deoxychlorinations with phosphorus oxychloride are therefore relatively slow and require a higher reaction temperature. It has been found that with phosphorus trichloride, 2 of the 3 chlorine atoms are available for deoxychlorinations, while with phosphorus pentachloride only 1 chlorine atom is usually used. As said, the resulting phosphorus oxychloride is much less reactive than the other phosphorus chlorides. Let's check some specific examples. Here, phenylacetic acid was converted into the acyl chloride with only half an equivalent of phosphorus trichloride, without any solvent. The product was purified by addition of benzene, followed by filtration to remove the precipitated phosphorous acid. Similarly, in this optimized example, half an equivalent of phosphorus trichloride was enough to attain a high yield of acid chloride. Here, toluene was used as solvent, what caused the precipitation of phosphorous acid. A further byproduct was the anhydride. In this example, the reaction rate was further enhanced by addition of DMF, what caused the deoxychlorination to proceed already at room temperature. One potential side reaction of the use of formamides as catalyst is Vilsmeier formulation, but this did not occur here. Phosphorus pentachloride is particularly well suited for the deoxychlorination of amides, as in this example. The resulting pyrazine is a highly electron-deficient heteroarene, and the carboxyl group thus particularly difficult to convert into an acyl chloride. This could nevertheless be achieved in only 2 hours at 80 degrees Celsius. Here, a glucose-derived acyl chloride was prepared by treatment of the acid with slightly more than 1 equivalent of phosphorus pentachloride in ether. The reaction already proceeded at room temperature. Because phosphorus pentachloride is a solid, solvents are usually required, and those listed here are sufficiently inert for this purpose. A number of examples have, however, been reported where even solid carboxylic acids were treated directly with solid phosphorus pentachloride, and high yields of acyl chloride resulted. This here is such an example. Here, solid tartaric acid was mixed with a slight excess of phosphorus pentachloride, and upon heating, the mixture melted and became homogeneous. All hydroxyl groups were substituted by chloride, and elimination of hydrogen chloride yielded chlorofumaroyl chloride. I do not consider it good practice to mix solid reactants without any solvent, because this can cause an extreme temperature rise and even ignition or explosion of the mixture. Interestingly, most deoxychlorinations described in this playlist are endothermic, sometimes strikingly so. But anyway, mixing of solid reactants is never a good idea and cannot usually be scaled up. For thermally sensitive acyl chlorides, phosphorus pentachloride may be the best choice because of its high reactivity. Here, for instance, a proline derivative was converted into the acyl chloride by stirring at room temperature for 30 minutes with just 1 equivalent of phosphorus pentachloride in chlorobenzene. The acyl chlorides of tertiary alpha amino acids readily decarbonylate to iminium chlorides, but this could be almost completely suppressed here by keeping the temperature low. This here is another example of a thermally labile acyl chloride. Tertiary alkyl etso compounds fragment upon heating into nitrogen and alkyl radicals and are used as foamers and radical initiators. This fragmentation may already start at around 50 degrees Celsius, depending on the precise structure of the etso compound. Here, a high yield of the target acyl chloride was obtained by treatment with phosphorus pentachloride at room temperature for 2 hours. Diacids that readily form cyclic anhydrides can be difficult to convert into dichlorides. Here, for instance, despite the high reactivity of the deoxychlorinating reagent, a large amount of cyclic anhydride resulted. A higher yield of dichloride would probably require a much higher reaction temperature. Unprotected enantiomerically pure alpha amino acids can be converted into acyl chlorides directly, as shown here. Neither the starting material nor the product were soluble in the reaction mixture, but the desired transformation occurred anyway. Phosphorous acid has a melting point of 73 degrees Celsius and can therefore often be precipitated with nonpolar solvents. Phosphoric acid, however, melts at around 40 degrees Celsius and is difficult to precipitate. Moreover, if deoxychlorinations are conducted with an excess of phosphorus oxychloride, as in this example, a non-volatile mixture of chlorophosphoric acids and anhydrides will result as byproduct, which can only be separated from non-volatile acyl chlorides by an aqueous extraction. This is in fact possible if the acyl chloride is sufficiently insoluble in water and soluble in non-polar solvents. Particularly suitable solvents for such extractions are dichloromethane or alkyl benzenes, such as xylene or ethylbenzene. These solvents only dissolve small quantities of water, and acyl chlorides dissolved in such solvents will remain unhydrolyzed for several hours. Less suitable are ethers or ethyl acetate, which dissolve quite large amounts of water. In the example on this slide, the authors used heptane for the extraction, also a good choice, but not all acyl chlorides are soluble in pure alkanes. So, what else can go wrong? If formamides are used as catalyst, then electron-rich arenes or CH-acidic compounds may undergo Wiltzmeier formulation. Unfortunately, even acyl chlorides can be sufficiently acidic to be formulated, as in this example. However, if phosphorus tri- or pentachloride are used, catalysis is hardly ever required. Phosphorus chlorides are powerful deoxychlorinating reagents, capable of converting carbonyl groups into geminal dichlorides or vinyl chlorides. Under forcing conditions or in the presence of catalysts, excessive phosphorus pentachloride will even turn acyl chlorides into trichloromethyl groups, as in the first example on this slide. Some esters are reactive enough to be deoxychlorinated by phosphorus chlorides already at room temperature, as shown in the second example. If one's starting acid contains such a reactive carbonyl group, a less reactive and more selective deoxychlorinating reagent should be used, for instance thionyl chloride, phosgene or oxalyl chloride. Generally, acyl chlorides or acylium cations will decarbonylate readily if a stabilized carbocation can be formed. Thus, activation of pivalic acid, phenylacetic acids or alpha amino acids can cause decarbonylation if the reaction temperature is too high. Transition metals such as palladium or rhodium can catalyze these reactions and even bring about the decarbonylation of otherwise stable acyl chlorides, for instance of benzoyl chloride. Thus, tertiary alpha amino acyl chlorides readily decarbonylate upon heating, as shown here. These acyl chlorides can only be prepared at low temperature with phosphorus chlorides or oxalyl chloride. A solvent of low polarity and high specific heat capacity may also help to prevent decarbonylations. Phosphorus pentachloride is an electrophilic chlorinating agent and may cause the oxidative chlorination of electron-rich or enolizable compounds. The first example here is the alpha chlorination of a nitrile, and in the second example a methyl ether was chlorinated. Then, if the starting acid contains too much water, deoxychlorination with phosphorus trichloride may yield bisphosphonates as byproduct. Phosphorous acid is a good nucleophile, and these reactions proceed by intermediate acylation of phosphorous acid by the acyl chloride. Any displaceable hydroxyl group in the starting acid may be deoxychlorinated, but can also be converted into a phosphide or phosphate. These are quite resistant to hydrolysis, and alcohols or phenols should therefore better be protected, also to prevent oligomerization of the product. Further potential side reactions include the formation of chloroiminium chlorides from amides and the dehydration of amides to nitriles. Alcohols may be converted into ethers or olefins. Even nitroalkanes can be dehydrated to nitrile oxides. Electron-rich alkenes or arenes sometimes undergo electrophilic phosphorylation under acidic conditions. With an excess of phosphorus chloride, the reaction mixture will turn strongly acidic, what can cause a large number of additional side reactions, such as debenzylations or rearrangements. Here are some more, mostly recent examples for further inspiration. Similarly reactive as phosphorus tri or pentachloride are isolated chloroiminium chlorides, but these only rarely offer significant advantages if compared to amide-catalyzed deoxychlorinations with phosgene, thionyl chloride, or oxalyl chloride. Then, as mentioned in part 1 of this playlist, geminal alkyl di or trichlorides are also occasionally used to prepare acyl chlorides. That's it. I hope you found this useful and stay tuned for more videos about practical organic synthesis.